The next thing that I'm going to talk about is some useful plots. I will have a more detailed session on plotting in base R later in this workshop. But at first, I just want to show you some commonly used plots, or not so commonly used, but still useful. The first one, the basic plot command, if you're putting in numeric variables, will give you a scatter plot. So the regression model I just fit was score tilde age. That's score as the dependent variable or response variable and age as the predictor. If I call plot with that same function as its argument, it will give me a scatter plot that is formatted like how I might want to see it if I was planning to run that regression model, with score on the y-axis and age on the x-axis, because that's convention for our predictor variable and our response variable. You can already see that there's maybe a couple of leverage points over here. Oh, you can't see where I'm pointing. In the upper left portion of that plot, which, maybe I would think about more if I was actually trying to analyze this data set instead of just show you some of the basics of what R can do. In the basic R installation GUI here, it popped up a graphics device that I can, resize as I want. If you're using RStudio, which is a very commonly used way of executing R code, then it will pop up in a plot in the little sub window on the lower right corner of your RStudio window. If I call the same function with age comma score, I get the same plot with age on the x-axis and score on the y-axis. The reason for this is that plot can take as one argument a score tilde age, and then it plots it in a sensible way for that formula with score on the y-axis. But it can also take x and y variables, and those then are in alphabetical order. So age x-axis and score y-axis are represented in the opposite order when they're separate arguments than they would be if they were a formula. That's sometimes confusing for people at first, but I think it makes sense because x comes before y when we're talking about them alphabetically, but the formula specification matches a lot of ways of talking about the general linear model with the response variable first. Given that I have a plot like this, with age on the x-axis and score on the y-axis, I can add a line to that plot using the abline function. There are many ways to use the abline function, but one very easy one is to put a regression model that we've already stored directly in it as its argument. And if I run this line of code, then I get a line drawn on my plot, which is the best fit line generated by the regression model that we ran a second ago and called model.1. It's important to note that model.1 had age as the predictor and score as the response variable, which is why this line is the best fit line for the points shown on the plot, but that's not, R doesn't check for that, right? So if this model used different variables, then it would just draw the line that would have fit those variables onto whatever plot you have active. And so it's not figuring out what you intend. It's plotting exactly what you tell it to plot when you tell it to plot it. So if you're in most ordinary situations, you want to make sure that you call abline immediately after the plot that has the variables that are referring to directly in the regression model that you're fitting. Often I'll just refit the regression model right in the call to abline to make sure I'm using the exact same variables that I called in the plot function. It's also useful to know about what plot does if you don't have a formula. So here I'm calling plot with just one argument that's a single vector. Model $1 residuals, remember, shows me a vector of the residuals from that regression model. And if I just plug that single vector into the plot function, then it gives me a plot of those residuals against their index. This is the order that they are in the data set. Well, it's not in the data set, but that the cases were in the original data set. So maybe not the most useful way to look at the residuals, but it's useful to know about what R will do if you just plot a single variable. It will plot its values in order. I can also say plot the residuals against age. So here I've done age, comma, model one $sign residuals. And so age is on the x-axis and the residuals are on the vertical axis or y-axis. And those two really high residuals up there in the upper left corner, those are those two leverage points that we saw earlier. The people who have a high score on this whatever this test is, but have a young age anyway. It's also useful to know about the QQ norm function, which plots a normal QQ plot of whatever argument is supplied for it. In this case, it's the residuals. That's a common way to use the QQ norm function. So here's a QQ plot of the residuals, and that might have called my attention to those two unusual points as well, showing up in the upper right corner of this QQ plot this time. I can also add a line to the QQ plot matching what you might typically see in a QQ plot using the function QQ line with the same argument. I would just call that function immediately after QQ norm in every instance. It just adds the line on top of the active plot. So of course, if you wait and do other things in between, then you might end up confusing yourself about which plot you're referring to. The histogram function is hist. So a histogram of the scores will show me this information. This is not an especially interesting histogram because there's only 20 data points, but I'll just call a histogram of MT cars $HP, the horsepower variable from the MT cars dataset, because it shows me a more interesting histogram where I can see some right skew, for example. And you can mess around with how many buckets the histogram uses by looking at the arguments that it takes. Now I want to show you how to do a linear model, a regression model, using categorical predictors. So I'm going to close out of this plotting device and call this line of code again, this function, which was the same as above, the summary of the linear model of score tilde age. And that gives me this regression model with age as the sole predictor. But let's say that I wanted to do to model score on the basis of gender instead. I could just run exactly the same code, but with gender instead of age. And R would give me output that makes sense. It shows me a single predictor called gender M in this case. If you recall, gender contains two values, F and M, well, 20 values that are all either F or M in this example. And here R automatically created a dummy variable where M is 1 and F is 0 for inclusion in the regression model. I can also do score tilde race, and R will automatically create for me two dummy variables, the appropriate number for race in this data set because it has 3 unique values, which were black, white, and Asian. It chooses Asian as the reference group because it comes first alphabetically by default, but I will show you in a little bit how to alter that. Those of you who are familiar with SPSS might already be seeing some ways in which R makes things convenient for you that would require a bunch of manual computations in SPSS, at least if you're using the standard regression function in SPSS. A note of caution for dealing with categorical variables. Hopefully this won't come up much for you, but if you're accustomed to coding your categorical variables using numeric indicators, like say I had a variable called numeric race, and it contained just this vector of 1s, 2s, and 3s, which happens to be exactly the same as the vector of values black, white, and Asian that I had built into my example data set. If I run summary of LM of score tilde numeric race, then I'm going to get this kind of result, where R fit a regression model with a single predictor, numeric race. It did not automatically generate the two dummy variables that I would actually like to see if this is how my data were represented. And the reason is that numeric race is just numbers because that's how I made it. That's how I constructed it a second ago in R. And so R has no way of knowing that I intended to use those integer numbers as indicators of categorical values. So it just treated them as numbers where 3 is twice as much as 1 and 2 is 3 is 3 times as much as 1 and 2 is 2 times as much as 1. That's not what I actually want, so I can use the factor function to convert this variable to a factor, a special data type in R, which is a set of categories with indicators. So if I just call factor of numeric race at the console, it will show me a copy of that variable, and it will enumerate the levels of that variable, the unique values, which is just how R displays factors by default. Note that this line of code did not convert numeric race to a factor. Uh, it just outputted a factorized version to the console directly. But I could instead store that factorized version in a new variable name called factor race, and then call the summary of the regression model that I wanted before. And here it has created 2 indicator variables for me once again, factor race 2 and factor race 3, using category 1 as the comparison group because it comes first alphabetically, just as I might have wanted it to do if this was how I was representing my categorical variable. A quick aside to talk about managing how R represents factors. R factors are quite convenient in a lot of situations. The race variable contained in the attached data set is already a factor, which is like a vector of integers that have string labels, or you can kind of think of it if you want as a vector of categories represented by strings. And I can see that it's currently a factor because when I print it to the console here, R shows me the enumeration of the levels of that factor automatically. There are other ways to tell. This is just one convenient one for short variables. Sometimes it's useful to call contrasts of a factor to see what variables R will construct automatically to represent that factor if you include it in a statistical model. And here I get a matrix representing the 2 indicator variables that I get by default. So one called black is an indicator variable where Asian is coded as 0, black as 1, and white as 0. And the column called white shows me that there will be a second indicator variable with Asian and black coded as 0 and white coded as 1. I'm going to detach data 1 for a second. Remember, data 1 is what's currently attached. So I'm going to detach it for a second because it's, for now, I recommend that you not alter attached data sets because the old version before your alterations will still be attached and it can get confusing. I am going to use the relevel function now to alter the comparison group for this variable. So data1 $race is the name of the vector that I'm inputting as the first argument to relevel. It's a factor. Relevel is designed to work with factors. The second argument, white, tells R what I want the new comparison group to be. And then the output of relevel I'm assigning over the top of the existing race variable in the data set. So now data1 $race contains a factor with white as the comparison group instead of Asian. If I attach the data again and then look at the contrasts of race just like I did above, I will see now that this matrix indicates 2 different indicator variables called Asian and black. Those are just the names of the indicator variables, but they are handy names because they refer to which category is coded as 1 for that indicator. And when I run my regression model, I get the same model or equivalent model, but this time with indicator variables for Asian and black, with white as the comparison group, which might be one way I want to represent the data in this example. The last thing I want to talk about in this session is what happens when you want to include more than one predictor variable in the same regression model. And the key symbols to keep in mind in most instances of specifying multiple predictors are the plus sign, the colon, and the asterisk. In the first example, I'm going to show you how to use the plus sign. So I've run this line of code just now, and here score is the outcome variable once again. But now on the right-hand side of the formula, I've got age plus gender instead of just age or gender. And R gave me a regression model with both of those predictors included, just as I would want it to. So the plus sign specifies multiple additive terms in a regression model. I can have more than two as well. So if I do age plus gender plus race, race is a 3-level factor. And so I get a regression model with 4 slope terms, 1 for age, 1 for gender, and 2 for race, just as I would like. The colon allows you to specify an interaction term in R, a multiplicative term. So if I want to see age and gender and the interaction between age and gender, I can call this line of code, and it will give me age and age colon gender as 3 additive terms, age plus age colon gender. And the colon tells R to calculate the product of age and gender in order to include an interaction term between those two variables. It's useful to know that this is what the colon does, because every time you see output involving interactions, there's going to be rows that are named with names that include that colon, which is the special character used in our formula specifications indicating an interaction term. But the vast majority of the time, you are not going to want to specify interactions yourself using the colon. Instead, you're going to use the asterisk. So if I do summary of LM of the formula score tilde age asterisk gender, then that is the standard interaction term notation. And it tells R that I want an interaction between age and gender, and I want all of the lower order terms that would be necessary in order to make that interaction sensible. So age asterisk gender automatically tells R that I want age, and I want gender, and I want the product of age and gender. And I want all of 3 of those added into the model as additive terms, which is just how you should set up this kind of model if you're testing for a traditional interaction term. If I do age asterisk race, then I will get, again, all the terms that I would sensibly want to include to test the age by race interaction, which is a single term for age, 2 indicators for race, and then 2 product terms representing age multiplied by the Asian indicator variable and age multiplied by the Black indicator variable. Remember that Asian and Black are the 2 indicator variables in this case because I changed what the contrasts, the default contrasts for race were going to be going forward in the last section. And if I want a 3-way interaction, I can do that by just including more terms separated by asterisks. So here I've got age, asterisk gender, asterisk race, and I get all of the terms that I would want in order to test this 3-way interaction, which includes both the first order terms for age, gender, and the race indicator variables, and the simple 2-way interactions between age and gender, age in each of the race indicators, and gender in each of the race indicators, and the actual 3-way interaction terms, of which there are 2, again, because there's 2 race indicator variables. If I wanted to have an interaction effect and what you might call a covariate in, say, in SPSS, I could do it like this, age asterisk gender plus race, and it works as intended, where race is added in to all the terms needed for the age by gender interaction. So I'm going to stop there for this session. Session 3 will pick up with the data and subsetting arguments that I alluded to before. And I'm looking forward to seeing you then. Hopefully that will be a live session, but we'll see if that works. If not, I'll just record it the way I've recorded this one.